welcome. My name is Rumbach. I'm a computational social scientist at the MZES, and I'm very happy to welcome today's workshop by Achterhold on algorithmic fairness. The Social Science Data Lab is an event series at the Munich Center for European Social Research that provides a platform for tools and methods for the collection, management, analysis, and visualization of data in the social sciences. The lead organizer is Dennis Cohn, and I'm very happy to be joining him in organizing today's event. About our speaker, Eva is a graduate student in human-computer interaction at LMU in Munich, and her interdisciplinary research interests include algorithmic fairness, which she will be talking about today, machine learning technologies, and social impacts of data-driven decision systems. The first part of the talk will be concerned with an overview to the general topic of algorithmic fairness and data-driven decision-making. And then in the second part of the talk, we will look a little bit at practical implementation of fairness metrics in AI systems. The talk is recorded. If you want to ask questions during the talk, please post a comment in the Zoom chat, and we will call on you after which you can unmute your microphone and speak. Please note that by posting your questions in the chat, we will read them out. This will be recorded. If you direct message us your comment, then this will not be recorded, and we will read them out anonymously. The recording will be posted on our YouTube channel, and so your questions will also be recorded. And now, having talked for a few minutes, I want to hand over to Eva. Thank you very much for being here today, and the stage is yours.
Thank you for the introduction. Okay, so I hope all of you can see the screen and the presentation, and yeah, welcome to my talk on the topic of investigating fairness and data-driven allocation of public resources, which is also my current master's thesis topic that I would like to introduce to you today. So as Ruben already said, we will start with the first part where I want to introduce some general concepts of fairness in machine learning, and then turn to the question of how fairness could be measured, and then going to introduce the use case that we're looking at in the second part, which is more kind of a live coding session. I prepared some code snippets in Python, which are also available in R, and we will go through the Python code together to see how these fairness measures can be calculated with these libraries that we're using, and then turn to the interpretation of the results that we obtained on the data that was generated by us. So let's start with the first part. And if you have any questions, just post it online, or you in the room can just ask questions in between. So to introduce data-driven decision-making, the general idea is to use large amounts of data from the past to find patterns under the assumption that things will turn out the same in the future. So as you see in the little figure below, you have some data, and then you apply a statistical model on this data, and the statistical model can vary in complexity, and then you get a decision, and there are systems where the model decision is taken and just like applied, but there are other systems where human intervention comes in, and there's a human decider in the end working with this data-driven decision as a support measure. And these methods are currently being used for risk assessment. For example, there's a quite famous case of Compass. That's a system that calculates the risk of recidivism. And based on this risk score, judges can decide if a defendant should be released or not. And there are systems that should predict long-term unemployment, which we call LTU, to allocate public resources, which is a topic or the main area of application for this talk as well. So there's a famous case from Austria where the Public Employment Service introduced a system in 2020 called AMAS. And the system should predict the integration chances of job seekers. So instead of predicting long-term unemployment, Austria decided to predict the reintegration chances of job seekers. And to do that, they had two criteria, a short-term criterion and a long-term criterion. And for each job seeker, both scores for the short-term and the long-term were calculated. And then based on the calculated risk score, or a more chance score of integration, the support measures should be allocated. So as you can see in the figure, if the IC score for the short-term criterion was above 66%, this person was assigned to group A and thus should not receive support, because the argument was that this person will likely be able to find a job without receiving measures. And then on the other hand, if in the long run, the predicted chances of re-employment are below 25%, then there's this group C who will be forwarded to external institutions for other measures than just like the common public employment service measures. So this group C got, for example, some psychological courses for supervision. And this system had human intervention because the IC score that is calculated was presented to the caseworkers, and then in the end, it was the caseworkers' decision on how to allocate the measures. But the system gained public attention because of a lot of criticism. When the developers published coefficients of the system, it was shown that being a woman or being non-EU member or citizen had a negative impact on your predicted integration chance. So this was a fairness consideration that arose because the chances for women to get support were lower than for men, for example. And then also the general decision to have a group C that will not receive public resources, but rather will be forwarded to external institutions, also was criticized by the public. And then further, the variables that the PES used to calculate the score were, for example, gender or age or other demographic variables, and also employment history. But in general, there's no agency for the job seekers to influence the score because, as you know, well, you cannot really change your age. And if the system says, well, you're 41, so your chances for reintegration are bad, then you as a job seeker have no agency to influence your score. And then also there was a lack of transparency and communication about the implementation of the system. So it was just introduced as a system that should be implemented. And then based on public attention and on researchers asking questions about the system, there was more and more information, but still some information is not public and cannot be addressed by researchers or others on how the system really works. And then there are studies showing that caseworkers hardly adapted algorithmic suggestions, which is a problem when you say that the decision that is made is not based on the algorithm, which would be a problem in law cases, for example, but that caseworkers still decide after the prediction was made. But then if the caseworker sees that the system might be right in 9 of 10 decision scenarios, it is difficult, or it's more likely that the caseworker will not decide against the algorithm for the 10th decision as well. And the system that Austria implemented for caseworkers to disagree with the decision of the algorithm was kind of complicated. So they really had to write a text why they think that the prediction is wrong. So it was not that easy to disagree with the decision. So what we look at now, or what is very easy or good to see with this example from Austria, is that there's not only the system implemented that can introduce bias, but there's a socio-technical environment in which these systems are implemented, and the socio-technical environment can already introduce bias into decision-making systems. So for example, if you look at the data generation phase, which is the phase before the algorithm is implemented, you can introduce or experience sampling bias, for example, or historical discrimination that is visible in the data. And then once the data is fed into the algorithm, this bias can be reinforced by the algorithmic system. And then in the data preparation and analysis phase, where you introduce the algorithm, you can have sources of bias, for example, in the variable construction, because, for example, most of these systems use gender as a binary attribute, which already is a simplified view on a very complex construct and can already encode discrimination. And further modeling choices, for example, or the error metrics you look at when introducing the system can already introduce discrimination into your system. And then as a third step, you have the implementation phase, which, for example, is the case of if there's a human decider, how much prejudice is in the human decider and can still be introduced even though the system might be free from bias or discrimination. And further, the decision rule in general on which the decision is made can still be discriminative, even though the model might be free from bias. So you have sources of bias and discrimination in the whole environment where the pure ML system is implemented. So it's not sufficient to just look at the technical implementation, but to also broaden your view on the context where you implement the system. Okay, so after introducing fairness, we want to turn to how can fairness be measured in algorithmic decision making. The first question we have to ask is, if we speak of fairness, towards whom should we be fair? And here we can differentiate between group versus individual fairness. So one idea could be to look at the averages over social groups. So you can say, okay, I want to be fair with regard to the group of people that share a specific attribute. But on the other hand, if you consider individual fairness, you could also say that you want to treat similar individuals similarly, which means that if two persons differ only in one attribute, for example, their integration chance should be very similar because all the other values are similar, which is why this one attribute should not account for the final decision. And as I already said, or as you see, we also have to talk about protected attributes. So protected attributes is more a term from law because there are several sensitive characteristics on which a decision is not allowed to be made. So for example, gender or age or sexual orientation, those are attributes on which law prevents decisions to be made in order to not discriminate. And in the context of fair machine learning, we use this notion of protected attributes to group together people or to identify those features which we don't want to have a high impact on the final decision. And yeah, with considering attributes as protected, there also comes responsibility. So the question arises that if it's only the attributes that we already have in law as protected attributes are sufficient to distinguish people, or if we should, well, focus on the individual more than on this group of people sharing the same protected attributes. So in this figure, you see that the general idea of you have information and you have a decision maker and then you have a decision is not new to algorithmic decision making, but is also present in human decision making. And when we speak of just decisions, what we have to consider is that even in human decision making, justice, the question of justice arises when it comes to the decision to be made. So even human decision making, for example, can encounter bias. And since, or as you see in this figure, this is not new to the use of algorithms in decision making, but the question of just decisions is existent even in human decision making systems. So as a measure to decide if a decision is just, we first have to speak about distributive justice principles, because there are several ideas in philosophy, for example, on what principle to follow if we want to have a just decision. You could, for example, say in the context of allocating public resources that you want to have a share of gender, if you assume gender to be binary, of 50-50 among women and men. But you could also say that in case women are harder to be integrated in the labor market, you want to give more support to women in order to help them being reintegrated, because just having a 50-50 share would not be sufficient, or it would not be fair, depending on which fairness principle you follow. So the question is how to allocate public goods in a just manner, and this question exists in any system that decides on the allocation of public resources. And what you already also have to think about is how to implement the decisions in the system. Do you want to introduce a human decision maker, or do you want to follow the algorithmic decision? These are questions that arise on the topic of just decisions. So to measure if a decision is just, we can, for example, use statistical parity difference, which I want to present to you now. So the idea of statistical parity difference is to look at the differences in selection rates between social groups. So if you imagine the orange circle to be one social group, let's assume it's the unprivileged, and the blue circle to be the other social group, let's assume that's the privileged one. You look at how many of the people in the group have a positive outcome and how many have, the share of positive outcomes in that group. So in our example, the orange social group has a share of 14 people with a positive outcome, and in the blue group, it's 9 out of 23. So the statistical parity difference is minus 0.11, which indicates that the privileged group has a higher selection rate, and this could be interpreted as unfair with terms or in regard to selection rate, and as preferences for the privileged group. And you can assess this measure either with a true outcome or with your predictions, because you have the selection rates in the outcomes that you have in your training data set, for example, but also in your predictions. This is why we have Z introduced as being either Y or Y hat. Y as the true outcome, Y hat as the predicted outcome. Have any questions on this, or it's clear? Okay. So what the algorithmic system now introduces to this process is that we have a feature set, which is the information, with a protected attribute we call A. Then we have a model that calculates a score, and based on the score and the threshold, the decision rule is applied. So what comes to this just decision question is now the question of how fair are the predictions of the model. And there we have to question which error metrics do we want to minimize, because once you have a model, you can look at where does the model misclassify instances, and if this misclassification rate, for example, is different between social groups, because you might want the model to be equally good on every person, no matter which protected attribute group this person belongs to. And so we want to ask whose errors are minimized in the process. And classical performance metrics are, for example, F1 score or accuracy. And what this fairness consideration now adds is, for example, the question of equal opportunity difference. And to come to equal opportunity difference, I want to show you the confusion matrix again, which is displays the error metrics of the algorithmic system. And so on the left, you see the actual outcome of an instance, and on the top, you see the predicted outcome. So for example, if the actual outcome is a positive one, which means that the person will become LTU, so positive is not the interpretation, but like a positive label, and the predicted outcome also is LTU, then you have a true positive. And as you can see, if the prediction, for example, is non-LTU, then the model is wrong and you have a false negative. And what you can calculate with these error metrics now is the true positive rate, also called recall, where you look at the proportion of actual positive that was identified correctly by the model. So you take all the actual positives, which is this row, and look at the true positives among all actual positives. And you can do that based on social groups as well. So you can now take your knowledge on the model's performance and look at the true positive rate per group, and then take the difference between two positive rates. So in this example, you see that the true positive rate of the orange group is 2 out of 4. So we have 2 true positives out of 4 actual positives. And in the blue circle, you have 6 out of 9. So in this example, you have the equal opportunity difference of minus 0.17, which is also negative, thus indicates a preference for the privileged group for this blue circle. So those are 2 measures, and they account for different stages kind of in the process. You have this fair prediction measure, which is only on errors made by the model. And then you have the just decision measure, the statistical variety difference that looks at the outcome and more like the implementation of the system in society. Okay, any questions so far? Okay, then I will turn to practice. And I want to introduce the data set that we use for the practical part now. So what we did is we generated 5,000 instances of job seekers. So it's just like our idea of job seekers, how they could exist, but there's no truth in it, kind of. And assume that the data collection was done by a third party, which is important because we have to assume that there's no sampling bias in the data, because we didn't access the data ourselves, but we just got the data. And so the possible fairness considerations that we have to think about is still historical discrimination, measurement bias, and data collection bias that could be present in our data. And our features that we have in our data set is one, the gender. So 1 is for female instances. Then we have age in the range of 16 to 67, because we assume people in the age where they should work or could work. Then we have last income, which is a positive value. We have occupation sector, where we differentiate between production and service sector. And we have data on the unemployment history of job seekers. So we simplified this to 1 means that this person was unemployed before, no other information, just information on prior unemployment. And then we have, long-term unemployment, and what you cannot see because of the Zoom.
Yeah, that's my fault, because I posted something to the chat. Maybe you can move it to the top.
Yes. Okay. So.
Yeah, just put it somewhere.
Yeah.
I will monitor the chat.
No problem. The targets that we predict is long-term unemployment, and based on this prediction, we derive the decision of if this instance should receive resources or not. And I'm going to present you a graph model where you can see the relations that we thought about could exist in this data example. For example, as you can see, we decided to have a negative correlation between the variable gender and income, which might exist in society. And for example, we also assumed a positive relation between gender and occupation sector, which you can see indicated by this green arrow. And we also introduced an interaction term between gender and age, because we assumed that at the beginning, the chances for the risk for long-term unemployment are similar for men and women, but then at a specific age, around 30, 35, there might be differences because of women might giving birth to children and therefore having higher risk of long-term unemployment. And as you also see, we have unemployment history that does not correlate with any other feature, and occupation sector does not have a direct impact on long-term unemployment, but correlates with other features that have a direct impact on long-term unemployment. And we set the decision threshold to 0.5, which means if the person has a risk score higher than 0.5, this person will receive resources in our example. Do you have any questions on this graph? Okay. So we will turn to the coding part now. And just to simplify idea of what we're going to do now. So we have this data that I introduced to you, and we will perform a logistic regression on the data and then calculate the equal opportunity difference for our example. And then we will have the decision values with a threshold of 0.5, and we will calculate the statistical parity difference on these decision values. And for the coding part, we use IBM's AIF 360 toolkit in Python, and this toolkit is also available in R. And I brought a list of other fairness packages in R that I found so far. So there are quite a few. And yeah, if you want to just play around with some of these packages, have a look into those. They are all accessible on GitHub. So you can have a look. All right. So I will open this link. If you want to have a look yourself, you can open the link as well. But we will do it together now. And yeah, you can ask questions, for example, on the coding part as well. I want to sit down for this. Okay, so this is a Colab notebook, which means these are executable code snippets that I prepared for this workshop. And yeah, you can just execute the code cell by cell and then look at the results. So what I'm going to do now is I'm going to first install the necessary package, the AIF 360 package. So I get a server space, and on this server space, I can do the calculations. And then next, I'm going to import the necessary packages that I need. And I'm not going to show you all the helper functions that I created because that's not that interesting.
Can I ask? So, I mean, this is a lot of code, but in general, you said we're just estimating a logistic regression model, and then using, like, if I was to do this now, I would just load the AIF library, run a logistic regression, and all the other stuff is probably
pre-coded kind of.
Okay.
Yeah. And you can run any other statistical model as well. So you could also do random forest, for example, or more complex models. Yeah, and then you can access the fairness metrics with help of the library that you're using. Okay. So
even if I don't understand what's happening in the Python code, that doesn't matter.
Yes. Yeah. And you can, I mean, that's the good thing about Google Colab. You can just execute the code. You don't have to know any of the Python code snippets. I also wrote down some explanation on what's happening in general. So yeah, it's kind of more a tutorial. You can get a first impression on Python, but I think it's quite the same for R as well. The methods should be the same for the AIF toolkit. Okay, so here we can see the first 5 rows of our data set with the features I just introduced to you. And what we do now is we set the relevant variables. So what we assume for now is that we have the sensitive attribute gender in our data set, which is binary encoded. I already talked about that this might not be sufficient or good, but we don't want to consider this at this point further. And then we have to define the privileged group and the unprivileged group. And let's just assume that in our data or in our use case, the privileged group is male, which is gender 0, and the unprivileged group are females, which is sensitive attribute gender, and if they have a 1. The target that we predict is long-term unemployment episodes. And as I already said, we just set the threshold to 0.5. So you could also change these values in here and, for example, look at another sensitive attribute, maybe age, for example, and also change the threshold. Because, for example, as I showed you before, in Austria, the threshold was, well, they had 2 thresholds, but one of those was 66%. So only if the person's integration chance, which is a different target, but yeah, is above 66, then we will not allocate measures to this person. So as you will see, the threshold is very important if you think about algorithmic fairness as well. And this area of thresholds is just to later review the importance of the thresholds that I'm going to show you. Okay, so the first thing we have to do is analyze the data, because we have to understand the data that we have at hand to understand the fairness implications and the fairness evaluation that we're doing. So we will first take a look into the distribution of our target variable in our data set. So as we see in our true outcome, we have a share of 70% that are not being long-term unemployed, and only 30% of our instances are being long-term unemployed. And then if we look at the distribution of the sensitive attribute, we see that we almost have a share of 60% male and 40% female instances. And next, what we can look at is the distribution of the target variable per sensitive attribute. So if we look at this plot, we see that in the group of not long-term unemployed, we have a share of around 70% men and 30% women. And in the group of actual long-term unemployed people, the share is kind of swapped. We have 40% male and 60% female instances. So this is just to get a first impression on the data that we're working with, just to know what we're talking about. So next, we're going to perform a train test split to later assess the performance of our model. And what I do here is create a binary label dataset. So that is just a class that the AIF toolkit requires. So we, just forward the information that we already have on the data, for example, a favorable label, which is again not favorable in the sense that being long-term unemployed is good, but it's the positive predicted label. And in turn, the unfavorable label is 0. We input the data frame, the target label, and the protected attribute, which is our sensitive attribute gender. And we decided to split our data by 70% of the instances that will belong to the training data set. Okay, and we will take another look into the training data set shape to see what has happened after the train test split. So we see that our training data set shape is of 3,500 instances with 5 features, and all the other information is also what we want. So we have the protected attribute gender, and these are the dataset feature names, for example, gender, age, occupation, income, and unemployment history. Okay, so now we prepared our data. So we are ready to learn a classifier on the data. As I already said, we're doing a logistic regression here. I can later also show you an example with a random forest that is included in this Colab notebook. But first, we will fit a logistic regression on our training data. And then we will get the predicted data set that comes from our logistic regression that we apply on the test data with the threshold set to 0.5. And what we do now is look at the confusion matrix I showed you before to get a first impression of the performance of our model. So as we can see here, this is the confusion matrix. So we have around 20% of true positive, which means that the model predicts LTU for actual LTU cases, or that the share of true positive predicted LTU is almost 20%. The predicted non-LTU and actual non-LTU is at 63%. And these are the errors that the model makes. So the actual LTUs, but predicted non-LTU, that's 10%. And we have 5% instances that are predicted LTU, even though they are actually non-LTU. So next we will have a look at the classification report, which gives us other metrics. As I already said, these are more common performance metrics that you use in machine learning. So for example, we have an accuracy of 84%, and precision and recall scores are, 80% precision and 68% recall is not too bad. That's just, also some general performance measures, how good the model is in classifying LTU and non-LTU people. So these results seem to be quite achievable. As a machine learning practitioner, you would say the model performs quite good on our data and is okay in distinguishing LTU persons from non-LTU persons. But these measures do not tell us anything about fairness. And so that is what we do next. We will look at the dataset metrics on our original test dataset, because as I already said, statistical parity difference also exists before we predict anything. So if we execute this cell, we see the distribution again that we saw in the plots in the beginning. And we also get the statistical parity difference of our original data set. So not the predicted data set, but the true outcomes, which is 0.2255. And now I included a little exercise in this notebook, and maybe we can just do it all together now. Because the question now is, how does this value, or how is this value being calculated? And I wrote down the calculation again. So the question just is which values I have to put here to get to the statistical parity difference of 0.2255. So yeah, maybe you can think about it, or also, write in the chat if you have an idea, or if you have any ideas, you can tell me if you want. What would you do to calculate the statistical parity difference of our true data now?
I know the answer.
So I just might wait a little bit if someone from the chat wants to guess or say what I have to do.
I'll start, and maybe I'm actually wrong. The first number would be 0.458, right? That's the proportion, and I would have to multiply the proportion with like actually LTU women is top left in that table. Or is it
No,
bottom right?
LTU is 1. Yeah.
Okay,
and
so bottom right.
Is also 1.
So
yeah.
it would be 0.184, and
Yes.
I need to, like, that's the percentage, so I would have to do I need to multiply that by the number of women in the data set, or can I just use the
No,
share?
you can just use the business.
Okay.
Yeah. Yeah, right. Because in this table we see that, as Roem said, gender female, the combination gender female and LTU yes is 0.184 in our actual data set. So this is, as you can say, the selection rate of women in our true data. And okay, I will continue now. So all women means, okay, what is the share of women in our data set? And this is displayed here. So we have 0.412, like 41% women. So we will put this here. And then we will do the same for men. So we will look into our cross table and look at, okay, gender 0, LTU 1, that is 0.130. And the share of men is 0.588. So if you execute this now, it gives us 0.2255. So I will later ask the question, what does it mean? But I will first finish the coding part, and then we can discuss on the interpretation of these values, because that's, I mean, the important thing, because we have a value now, but we have to know what this value really means. Okay, so next we will look at the classification metrics. So this is the part where the predictions of the model are being important now. So we will execute this cell. And what we get is, again, just distributions, the true distribution again, LTUE and gender, and then this cross table. And what we also get is the predicted distribution. So we have the LTU predicted scores and the distribution of these, and then the cross table, gender, and the LTUE predictions. And what we also get is a confusion matrix per group. So we see for each social group, where does the model make more errors? So you can, for example, see that the true positive rate for women is 30%, whereas the true positive rate for men is only 14%. And what you also see is that the true negative rate, in turn, is 46% for women, but 76% for men. So, I mean, these are both, the diagonal are both true predictions. So it's not that easy to decide if the model makes more errors in one group, because, I mean, although here the true positive rate is higher, the true negative rate is way lower than for the men. And we get some classification metrics as well. So we have the more common performance metrics, F1 score, which is 73%, and accuracy 84%. We have again the statistical parity difference, but this time it is for the predicted labels, not for the true labels, but is similar to the ones in the true labels. And we have the equal opportunity difference of 0.0145. So as a next exercise, I wanted to calculate the equal opportunity difference with you as well. But I can just scroll down to here. Like that. So if you want, you can again look at the data, or yeah, tell me what you would do to calculate the equal opportunity difference now. I mean, it might be a bit difficult because we do not see all the values now, but well, I might keep this for you if you want to have a look at it on your own, because I forgot to delete the values anyways. So yeah, we look at the true positives for women, which is 0.3042, this true positive value. And since we need the true positive rate, we have to divide this true positive by all positive women, which is true positives plus false negatives, I think. Let's see. So that's a little bit confusing with this confusion matrix. So we have predicted non-LTU, but actual LTU, which is a false prediction, and the false prediction is negative, which is why this is a false negative. So you look at the share of true positives among all actual positive women in this case, and you do the same for men. So if we execute this now, we have the value of 0.1045. So yeah, with these values, I want to go back to the presentation now, because as I already said, what is now important is to interpret these values. So what does it mean if we have a statistic parity difference of 22% and an equal opportunity difference of 0.0145? I'm going to start the presentation again. And we will turn to the interpretation of these values. So the questions that we have is, what do the fairness metrics tell us about the predicted LTU risk score for each social group? And does the ADM process discriminate against women in our example use case? What would you say after seeing the statistical parity difference and equal opportunity difference? What do you think? What is your first impression?
The values were all positive, right?
Sorry?
The values were all positive. Or was it only
Yeah.
the first one? Yeah.
It was positive, yeah.
And women was in like the first part of the equation.
Mm-hmm.
So doesn't it reflect kind of the share in the end of people? And so basically it wouldn't discriminate against women.
Mm-hmm.
Is that
okay? So you say because the values are positive and women are the first part of the equation, it is not discriminative against women because it's positive. Okay. Yeah. Yeah. So the equal opportunity difference was close to 0, kind of. So would you still say it's, what's like your interpretation of that? Is it fair?
If you ask me that way, kind of in these metrics, have you already put some assumptions on kind of what you expect?
Oh, not really. I mean, you look at the model outcomes per group and only the true positive rate. So maybe you have the assumption of only looking at the true positives, which is already the assumption of the share of people that actually are long-term unemployed. How good are these detected? So what you have to keep in mind is that this metric doesn't say anything about the people that are actually not LTU, because when you remember the confusion matrix, you just look on the upper row, but not on the bottom row, which is the people that are actually non-LTU. So yeah, it is kind of a pre-assumption you have, right? Because you focus on one outcome and not focusing on the other.
Could you maybe go back to the like calculations of these rates that you showed earlier?
This?
Yes, for example. So equal opportunity difference that was very close to 0.
Mm-hmm.
And that is actually, so we have predicted for unprivileged and true one minus predicted one for privileged and true one. And so if this is very close to 0, then we would probably say, well, from this perspective, it's fine.
Mm-hmm. So what exactly is this perspective?
From the equal, if we take this measure of fairness, mm-hmm. then we would say, well, this is fair. There's no discrimination.
Yeah. So we would, or we might say that we have fair predictions. If you think about the figure I showed you before, because with this being close to 0, we could say that at least for the true positive rate, we do not differentiate between groups. So for the model to detect those persons that actually become long-term unemployed as such, the attribute gender doesn't seem to have a great effect on the model's predictions. But we have a statistical parity difference of 22% in our true data as well as in our predictions. So what we think about that, is that fair?
Discriminating against one group.
Which one?
And my intuition was that it's actually against men. Is that correct?
Yeah, it's a positive value, which means that the selection rate for the unprivileged group is actually higher than for the privileged group. And since we declared women as unprivileged, the selection rate among women is higher, yeah. And would you say that the algorithm introduced unfairness?
Alex, do you want to respond? Otherwise, there's also a comment in the chat. So it depends. Unai says it depends on what we want the model to do. If we leave it as it is, we would reproduce the historical bias we see in the data, and this might be unwanted.
Yeah, that's kind of true, because we saw that these differences also exist in our true data and are very similar after applying the model. So from my perspective, or one interpretation would be that the discrimination that is present in the society is reflected by the model, but not reinforced. So the problem that we face might not be the introduction of algorithmic profiling or data-driven allocation or any algorithmic decision system, but the problem lies in societal discrimination that we face, no matter if we have human deciders or algorithmic systems deciding.
That's the problem. If you believe or if you follow that prediction, then you reproduce it. If you not introduce it, but you reproduce it.
Right. So you can still debate on if there is discrimination, do you want to reproduce it, or do you want to have a normative objective, or like, do we aim as a society for a different world in which this discrimination that is present right now should not be reflected by algorithmic decisions?
So we could say at least we are not making the situation worse, but we are certainly not changing anything towards a more fair society.
I wouldn't say that, because I think reintroducing or keeping existing biases could still change to the worse, or you know, because that what is present right now would be still present in the future and might even become stronger, even though the model's decision do not introduce additional discrimination. But since we do not change, we cannot say that it is or it stays as bad as it is, because there could still, I mean, anything could happen that we enforce or reinforce these biases or even strengthen them. My personal opinion on this. So yeah, I think, well, let's just continue with the presentation first, and then we can have another open discussion, because I think that's the interesting part of this whole topic, to discuss on such values and moral norms that we have when introducing these systems or asking these questions. Okay, so to sum up, we looked at the statistical parity difference, and the aim of this, or the general idea, is that the prediction should be independent of the sensitive attribute, in our case, gender. As I already said, you can still look at the statistical parity difference in the true outcomes, but for the prediction, the general idea is that, or let's say the decision should be independent of this protected attribute. But we see we have a positive value, which in turn means women are more likely to be labeled long-term unemployed. And with our decision rule of giving support to those that are being predicted as long-term chances for support. And for equal opportunity difference, the aim is that true positive rates should be equal for social groups. And since we saw that our equal opportunity difference is around 0, we can say that the model can equally well detect actual positives for men and for women in our example. So we started the discussion, but asking, does the process discriminate with the values that we just saw? We can say, okay, women are more likely to be labeled long-term unemployed, which means that they have higher chances of receiving resources. So one could say that this process doesn't discriminate against women, but against men. But you have to think about also, like, where does this value come from? So we saw that the statistical parity difference exists because in our data set and our actual data, we see that women have higher chances of becoming long-term unemployed. So our decision to support them with measures for not being long-term unemployed could be justified by the existing difficulty of women finding re-employment, and thus could be justified in the socio-technical environment again, to have different values or different selection rates between men and women. So the general question that I want to ask is, what do we achieve with statistical parity difference, or what is our perfect statistical parity difference? Because just because this value could be 0, we still have to think about, okay, even if this fairness measure is balanced or has the perfect value in the process of allocating measures, is this even what we want to achieve? Is the statistical parity difference of 0 our social goal, kind of, you know? Because I think what's problematic and what we already talked about is that with these fairness metrics, it seems easy for some people to say, okay, since we achieve good values, we have a fair algorithm and a fair algorithmic implementation. But that's why I really want to highlight the interpretation of these values, because just because the value is 0, we cannot say we have a fair product or a fair process. Because you have to look at what do we have right now in society, what does our process add to the existing processes, and what are the consequences of our algorithmic decision-making system, or what are the flaws that we already experience in the existing systems. So yeah, we really have to look at the bigger picture and the whole context in which your system is implemented. And then the equal opportunity difference, as I already said, is almost 0. So the true positive rates are almost equal across social groups, which means that given someone needs resources, because we look at the persons that are predicted or that are actually long-term unemployed, gender is not a factor for actually receiving them. Do you have any questions on this? Or comments? I mean, it says, yeah.
Actually interpret the magnitude of these values, and it will be kind of percentage over, like.
You mean interpret in terms of when at which value it could be fair, or?
No, I'm just meaning the magnitude, or is that?
I mean, yeah, you can.
Like what you said, I don't know, it discriminates against women by 20% or something, or is that how that's reported, or?
No, I think I would be careful with saying like that it is discriminative by 20%. Because I mean, that still is difficult to understand, right? How to have a magnitude of discrimination. That is why I would stick to the, what does it really say? Like, as I said, for equal opportunity difference, given someone needs resources, so we only look at the persons that are becoming long-term unemployed. We see, for example, if we would have a higher equal opportunity difference, we can say that the chances for being predicted as such are higher for one group than the other. But I wouldn't frame that in terms of 50% higher because we have equal opportunity difference of 0.5. Because, yeah, I think this still is you have to be sensitive on how to communicate discrimination, because saying like that is 3 times more discriminative against women is kind of, what do you mean by that? So I would stick to the actual, the actual information that is visible with this metric, but not having a easier interpretation, kind of. Does that answer the question? Okay. What I also want to say, like before open discussions, is what can we do next? So what is the outcome that we can take from this? First thing is we have to consider long-term effects, because that was what we kind of talked about. If we just represent what is there with algorithmic systems, what does change in the long run? And what you often read is about feedback loops, because, for example, supporting women now with more support than men, for example, can result in change of data generating process, which then leads to achieving statistical parity difference, for example, in the long run, because supporting women with more measures right now could lead to more equality in training data and like the statistical parity difference of actual labels. And then a model that is trained on this more balanced data set would also be more balanced in predicting or in selection rates and predicted values. Or it could happen. It doesn't have to happen like that, but you know, the argument for supporting women with more measures right now, even though statistical parity difference is not ideal, could be that it could change, or it could introduce fairness in the long run. Then another idea is to include model uncertainty, because you could say, for example, that, I mean, you have some individuals which are classified with kind of a high probability value, and then you have individuals which are very close to the decision boundary. So focusing on these individuals, and for example, think about, okay, you could say that the algorithm should decide on people that are easy to classify, kind of, but when it gets more complicated, or people that are close to the decision boundary, those should be forwarded to the caseworkers, and those should be assessed by human decision makers with expertise, for example, with skills or with additional information. So you could split the data set again into people where the classification is more clear than for others. And that could introduce fairness again, because often it is especially the people being very close to the decision boundary. As I already said, maybe there's, for the variable age, just 1 year, and you're 1 year too old, and then being classified completely different than if you would have been 1 year younger. Then what I want to also highlight is that we have to involve interdisciplinary research into the whole topic of fairness in machine learning, because we can draw on insights from social sciences, philosophy, and law, and many other disciplines. Because as I already saw, we have philosophical ideas of distributed justice in this. We have people from law that had to deal with discrimination by any decision-making system for years now. So the general idea of discriminative decision systems is not new to algorithmic systems. Then we have machine learning practitioners who think about fairness-enhancing interventions, for example, how we could make algorithms being aware of discrimination that is present in the training data, and which methods could be implemented to also account for these biases in the pre-processing, in-processing, or post-processing steps. So there are many ideas how to account for bias in the whole machine learning cycle that aim for ensuring non-discrimination through these processes. And of course, social sciences have a lot of knowledge on social constructs, or also these measurement biases, sampling biases. Those are metrics, or those are difficulties that social scientists know about. And so, yeah, I think it's very important to have many disciplines looking at this topic together, and to engage in public debates, and especially involving those who are affected by all these systems, involving those in the discourse, because I mean, the difficulty, especially when you think about the norms that we want to ensure with these systems, or if we want to change, for example, outcomes to the better, someone has to define the better or the fair outcome. And the people that decide on the fair outcome should not be those who are not affected by the systems and by the unfair outcomes. So it is very important to place this topic in many different disciplines and areas and societies or social groups to inform people on the difficulties and to let them think about, yeah, maybe their personal and social norm or their ideas how to solve these issues. Do you have any questions on this or any comments? Okay, then I think, yeah, this will be it for now. So we can, of course, still discuss on the topic, or if you have any ideas, I'll be open to hear them. Or if you want to see, for example, more coding snippets, maybe the random forest classification, I'll be open for that as well. So
Yeah. Thank you very much, Eva. First of all, very nice talk. So, yeah, I think we'll just see if there are questions from the chat and from the group here. I don't know, Alex. Yeah.
Very interesting. Thanks a lot. One question I have is, you simulated data, right? But wouldn't it be also interesting to kind of understand what the actual settings are? For example, you presented the case in Austria. Is there any way you could get kind of, or are there other plans to get these data, or kind of at least understand what are the patterns behind these data?
yes, so I know that there's a data set of unemployed in Germany, which Ruben worked with, and for my master's thesis, I got a data set of job seekers from Austria, actually, young people from Vienna, and I am trying to mimic this AMS system or AMS system on the data set of young job seekers in Austria, but we couldn't use this data for the purpose of presenting it because of data protection and everything. But what still is difficult, and as I already said, communication on the systems or transparent communication of the systems is very rare. So the AMS, for example, they use the stratification procedure, not a logistic regression, to classify the individuals, but you don't have any information on how the groups were formed or on the training data they had or the data they had at hand when generating this algorithm or deploying this algorithm. And now they have published some coefficients, which I'm using for my master's thesis to assess the fairness of this AMS model, but it is still very difficult to achieve similar results as reported, for example, for accuracy and to assess fairness on this specific algorithm, because you have such few knowledge on the actual implementation. So I think it would be necessary to also, of course, evaluate systems that are already in use, as done with this compass system, this recidivism score. There's a data set, and there's also knowledge on the model, and journalists try to reproduce this algorithm, but I think it still lacks lots of transparent communication, one on the data and on the algorithmic implementation, and to assess fairness of systems that are being used.
There's also a question in the chat by Unai, and he asks whether you've seen any work where people try to explicitly model feedback loops and the impact of decision-making on the data generating process.
I haven't seen work so far, but I think there's some proposals in this agent-based modeling where people try to model feedback loops. So they have agents and they have specific attributes, and then there's the decision that is being done on these agents, and then you can simulate years and years of decision-making processes and changes in society. I think, yeah, social scientists also work with agent-based modeling. So definitely there are attempts to used this procedure for also simulating feedback loops, but I don't have any paper recommendation, unfortunately. But I can look it up and just send it afterwards.
Yeah.
But I think that's very interesting to look into how exactly these feedback loops can reinforce, for example, biases, or maybe ensure fairness as well. Yeah.
Yeah, I think related to that, like the question is, I mean, this is like we can do it with real data. We could train a system and see predictions, but in the end, what we need to do is to understand the impact. We would probably need to run some experiment, or at least in a simulated environment with agent-based modeling.
Yeah. And I think what is also interesting, some people suggest, for example, one suggestion is always to just remove the sensitive attribute from the prediction and from the feature space. But that is quite interesting to see in our graph, because what we did is we introduced some correlations that are not explicitly, or yeah, we have the direct relation between gender and our outcome. But for example, if you imagine removing gender from this, you still have gender encoded, for example, in the income. Just thinking of the gender pay gap, for example, even removing the attribute gender could still encode discrimination based on the attribute gender, even though the model has never seen this attribute. And another thing that people always tell me when I talk about this is, for example, yeah, if there's historical discrimination on the labor market, why aren't you training your model on data from last year? Because then you don't have historical discrimination. But in my opinion, the term historical discrimination doesn't mean we're looking at data from the 70s or so, but another, or again, gender pay gap is a good example, because I would say that it's historical discrimination, but it is still encoded in the data that we obtain these days. Or for example, yeah, differences in work or re-employment because of giving birth to children. That is kind of, it has its roots in historical societies, but it is still present in our society. So it doesn't mean historical discrimination that I look at data that is like 50 years old and that women are discriminated against, but these discriminations are still encoded in our societies, even though their roots are a few years ago or a long time ago, kind of. And so, yeah, I think what is important is to update the algorithmic systems now and then, or routinely, to have changes in society also reflected by the systems. But that kind of, I get the feeling that is done, or that is commonly done, that it's not new to machine learning practitioners to update their systems when the training data is updated. That's a common process, but society has to change in order to change training data, in order to change the algorithmic system.
And I think exactly like these kind of relationships, that's where people like us working in large social science departments and studying labor markets, studying discrimination, understanding the processes that even if everybody wants society to be fair, it's still unfair. That's where like our expertise is needed.
Yeah.
And I mean, this is a technological question, but well, part of the story is a technological question. And so far, most of the work in this area is probably done by people in computer science, but that probably gets us to exactly the situation where these questions are ignored.
Yeah, definitely. Yeah. And I mean, a computer scientist, in general, the aim is to reflect the data you have as good as possible. So telling the machine learning practitioner to change the data in order to not discriminate against a social group is somehow contrary to the general aim of machine learning processes, to reflect what you see in the training data to the best you can. So yeah, it's very important to, as I already said, bring different disciplines together to join knowledge and also like objectives, and to have, yeah, a general ideological maybe objective, because as I already said, it's a socio-technical system. It's not the machine learning model itself that introduces discrimination.
I have a quite related question. You mentioned, I mean, there are so many other applications where this can be applied, not only on algorithmic decision making, but also in other settings. Would you say that these metrics can be used in general to kind of, what's the term, that kind of data bias or so, right? Can you use more generally, or maybe these metrics represent or other metrics?
Yeah, well, I would say, as I already said, statistical parity difference, the idea behind is somehow unique, not unique to data-driven decision-making systems. It's just like, okay, let's look at the share of people that get something, or of one group versus people that get something or doesn't get something out of the other group. So yeah, I think you can take these metrics, the just decision metrics, to other domains or areas, but the fair prediction metrics are kind of model specific or more like machine learning specific. So I would differentiate between which metrics you want to take over to other areas, because I think it's possible for the just decision metrics, but not for the fair prediction metrics. But for example, there's another just decision metrics called disparate impact, where you take the ratio, not the difference of selection rates. And that stems from the legal sciences, because there's this 80% rule in law, which says that the rate of persons from one group that are selected is not allowed to be less than 80% of the rate of persons from the other group. So the notion of disparate impact comes from law and is then being implemented in the technical systems. And so, yeah, you can use these metrics in other disciplines or other application areas as well.
And maybe one final question, and then we're also coming to the end of this data lab today. So, I mean, we are talking about bias in machine learning and unfairness, and we're treating the situation as if this is all a problem because we are using algorithms. But I mean, today, such decisions are made. They're just not made with algorithmic help. So how would you how would you discuss that in light of the whole using algorithms, in light of we are already doing this just another way?
So my personal opinion is that these algorithmic systems reveal or quantify discrimination that is already present in society, because we're talking about discrimination now. I mean, it's not new that processes in society are discriminative, but it was just like kind of accepted by most of the people. But now that we want to use algorithmic systems, and we have, for example, these coefficients in the Austrian case, we have a measure of discrimination and that we can discuss on. So I think the problem is not using algorithms. As I already said, the discrimination is already present in society. And what changes now is that I think it's kind of easier to introduce a normative objective in algorithmic decision-making than retraining or debiasing humans. So that is kind of my personal advantage of technical systems, that once we decide on a world where we want to live in or how we want the world to be, we can introduce this into data-driven decision-making systems, but changing purely human decision makers is very difficult. But I think, yeah, what is necessary is more like in the context of allocating public resources, to really decide on who do we want to support, and can we even measure the need for support just by predicting long-term unemployment. I mean, this take this to decide on receiving resources, but there are so many variables that can still come in between this or in this black arrow area. So yeah, I think machine learning is a tool to ease and to maybe be more cost efficient on allocation of public resources, but it's not a solution for anything. And it is neither discriminative in the process itself, nor can it solve the problem of unfairness in allocation of resources. So it's kind of in between, and like I have the feeling the more I talk and think about it, the bigger the problem is. So yeah, I hope I could give some of my open questions to you today, and you would think about it, and maybe you come up with other ideas or interesting thoughts. I think it's all about discussion of this topic.
Nice. Thank you very much. That's a very nice closing statement. And yeah, thanks again for joining us today on this very interesting and also very prominent topic. And yeah, that's it for today. Have a look at Twitter, have a look at your emails to stay up to date for upcoming events in the Social Science Data Lab. And with that, thank you all very much for attending and hope to see you soon.